Hiya. We're now in the grace period after the assignment's due, but this is a little routing video for those of you who are having some trouble debugging. So my original plan was to not do any kind of video about routing unless there seemed to be clamoring for it, and there didn't seem to be any people pinging me to say, hey, where's the video? But now looking at office hours and Piazza, it just seems like there's clearly enough struggle somewhere that it's worth putting out here. So basically what's going to happen in this video, I'm going to talk about some of the most common bugs. I'm also going to talk about the 4 most common implementations for A-star, and basically what I did is I just looked at a bunch of student code and got a sense of what are people trying, and you might find it useful to identify which approach you came up with, or that you're working on, so you can compare what you have to the others, or maybe you can change implementations entirely. Now if you're somebody who's starting out routing, this video isn't really supposed to be an introduction to A-star or routing, but I will mention that approach 2 seems to be the easiest to get right, and I should also mention that there's an old saying that premature optimization is the root of all evil, and that's definitely the case with this project. There's a lot of little things you can try and do to speed up your code that can actually break your code, so I would keep it as simple as possible, start with functionality, and then try and speed things up. So I should mention what the known student approaches are, and then I'll say a few common bugs, and then I'll have a few separate smaller videos about each of these approaches. So the 4 primary approaches are as follows. The first approach is similar to what's in lecture. And the difference between the approaches is simply what starts in the fringe, whether or not you can add vertices to the fringe, and whether or not you update priorities. So approach 1, which is the same one from lecture, you start with everything in the fringe with infinite priorities, and you never add a new vertex. Everything is there originally, you never add new things, but you update priorities. Approach 2, which is the same as in homework 3 or in the Peter Abil videos that were linked in the spec, in that approach you start with the fringe having only the source, you add new vertices to the fringe as you see them, and you never update any priorities in the fringe. Like, once a vertex is in there, it stays that way, it is forever. And then approach 3 is a somewhat of a hybrid of those ideas, where you start with only the source, you can add new vertices, but you can also update priorities as you go. This seems to be a somewhat less common approach than 1 and 2, and then there's finally approach 4. Now approach 4 is really just approach 2 in disguise, but in that case what you do is you attempt to adapt puzzle solver, and I'll have some notes at the very end of all these slides, and that'll be the last of the videos here. But that is going to basically just be homework 2 in a different flavor. So for approaches 2 and 3, you might have tried to create a marked vertex set that keeps you from ever revisiting old vertices, but I'll say that the reference solution, even with that part of the reference solution commented out, runs perfectly fine. So you don't actually need a mark set to pass the autograder, but in your case, depending on how your code works, you may need to add it to pass the most stringent of the timing tests. So a couple general notes. I want to say that any approach, no matter which of these you do, or even if you do something else that's weirder, any approach is going to involve relaxation, which I also sometimes call better than checking. This is where, sorry, microphone was over there. It's better now. Anyway, this approach, what it does is it will, I got distracted by microphone. So any approach you do for A-star is going to involve relaxation, which is also sometimes I call that better than checking. And that basically says this, okay? Suppose the vertex we've most recently dequeued is V, and we're considering all of V's neighbors, and one of those neighbors is W. Well, we relax this edge from V to W, and that basically means this. So since W is a neighbor of V, we say, is the distance from the source to V plus the edge weight from V to W, is that better than what I've already stored for the best known distance from source to W? Okay. Now here DSV refers to the entire path from S to V, and we have that stored in some kind of data structure I'll call best. ED is the Euclidean distance from V to W, it's the edge weight from V to W. And that overall sum, if it is better than what I've got stored in my best known list of distances, then I'll update best, and I will also update the fringe. In each of the different approaches, I'll have a little more verbosely, but this is the fundamental operation at the heart of all of our A-star implementations. Now here, DSV is the best known distance from S to V. Again, it's the whole path. This needs to be stored somewhere. We have our our Euclidean distance from V to W. This is also the edge weight from V to W. And then there's also the Euclidean distance from W to goal. This is our heuristic. Now you'll notice that when it comes to relaxation, we don't take into account this Euclidean distance. That's actually only going to be in the fringe, which is used to decide the order of the vertices that we consider. Okay. Now best, right? What is best? I'll also talk about what fringe is in each approach, but in best, it's some data structure that needs to keep track of those best distances. How do I get from S to V, S to W, S to A, S to whatever else? And it also needs to keep track of the parent of every vertex. So if the best known path to W is through V, you need to say edge to W equals V. Now in lecture we used an edge to array, but that doesn't really make sense for this assignment because our vertices are not numbered 0 through V minus 1. So you'll just need to keep track of this information somewhere. So I think the easiest idea is to have two maps. One that maps from vertex number to best known distance, that would be DSW, and the other that goes from vertex number to best parent vertex, right? So edge to W equals V. So you can think of this as, instead of best vertex number, you can also read this as parent. Now students did other things, right? For example, you can take your graph DB and have those actual nodes store information about their parents, their distance, and that will work fine too. You just have to be a little careful. So let me just talk about some of the most common tricky bugs, and you can think about these. Now, if some of these don't quite make sense, you may find it helpful to look at the simple or the approach by approach videos that are going to come after this little sub video. So I'll just enumerate these though, okay? So some of the most common bugs that I've seen in office hours or on Piazza are, first, whenever you need to set your distance in your best data structure, this is like you're storing the best known thing, some students will say the distance from S to W is the distance from S to V plus the Euclidean distance from V to W plus the heuristic distance from W to goal, right? This right here. Now that's not a good idea because the distance from source to W should never include H of W and best. This H is only going to be used when we're thinking about the fringe and never with best. It's a subtle point, but an important one. Similar, the opposite of that problem is not including the heuristic distance to the goal when you're trying to decide the priorities of nodes in the fringe. Now that'll actually work correctly, but it's Dijkstra's algorithm as a result, and thus it's slow. So this will actually break functionality. This will just make your code slow if you forget to use H of W. Okay. A third bug that's very subtle and hard to fix, or actually not call these hard to fix so much as like hard to spot. Okay, so this is a hard to spot issue. Okay. They're actually pretty easy to fix for the most part, but they're hard to spot. A third one is changing priorities of objects inside of a Java util priority queue. So I take a node, I enqueue it in a priority queue, and then I have a reference of like a handle to that node, and I change something about its priority, and that can result in the wrong node being returned by poll. Now actually it's possible, depending on how your priority calculation is done, that maybe you're not explicitly changing something in your node object itself. Maybe you're changing something in best that causes the effective priority to be changed. But basically the point here is if the priority of a node inside of Java util priority queue is changed, that can cause bad things to happen. You might get back the wrong node. Okay. Fourth, if you use a marked set inappropriately. So for example, if you mark when a vertex is added to the fringe, your code will break. And you can see here if you did that in the approach 2x slides. And then finally, another really common bug that's very hard to spot is letting shortest paths mutate your graph. And by mutate, I mean change it in any way. So commonly, a bug is you run shortest paths and it sets a bunch of previous pointers, and then you run shortest paths again and all those previous pointers are still there, and it can actually break the run of shortest paths. So what I say is that when shortest paths completes at the very bottom of your method, your GraphDB object should be exactly the same as when it started. And you can do that by giving your GraphDB object some kind of reset method that you always call at the end that makes sure that it sets all of the instance variables back to their start. Now, I'm not a big fan of that because I think it's better for shortest paths to own the information about the search and not GraphDB, because a GraphDB is a more general thing than just a shortest paths object, but you're welcome to do it. We're not going to penalize, but just be warned that letting a method mutate an object can be dangerous in general. Okay, so that's it for this little tiny video about the most common bugs. What's going to follow is I'm going to go through each of the approaches. So if you want to actually, if you're still having some trouble, figure out which one of these approaches you're following, and then go to the video that corresponds to your issue. And I guess I'll add a link to this slide so that you can easily find the video that has to do with your implementation.